Hello and welcome to this vSuite version 0.6 video tutorial. And in this video tutorial I'm going to cover just the very basics of doing a radiance lighting simulation with the LiVi component of the vSuite. So I have set up here an extremely simple scene, and I'm picking this simplicity of scene just to keep everything quick for the video. And the particular geometries that I'm using here are quite effective at showing some of the effects of options that we have when we're exporting Blender geometry into a format that Radiance can understand. So I've got a sphere, and I'm just going to check what materials. So I've got a standard material associated with the sphere, and I've got the same material associated with this plane. So I'm just going to create my nodes that I'm going to require for a simple LiVi analysis. So I'm going to require a VI location node, as I did for the shadow study mapping in the previous video. And now I'm going to need a LiVi geometry node, and I'm going to need a LiVi context node. So the VI location node, for the kind of simple radiance analysis I'm doing here, we can have manual or EPW for the latitude and longitude. So I'm just going to stay on manual, and I'm going to connect in my VI location node to my LiVi context node. And once I've done that, I now have this export option down here. My LiVi geometry node, I don't require any node inputs to this, so I can just click export, and now I have a LiVi geometry set up, or a radiance geometry set up, and I have a LiVi context or a radiance sky set up. So let's now add in a LiVi simulation node, and I'm going to connect in the geometry and the context. And I can't remember if I've said this in a previous video, but you should now notice that nodes often start red. And if they're red, that means they're not yet ready to be part of a simulation. So usually clicking on the export button or a simulation button will turn that red node into the default color, and then you know that that node contains valid data, which can then be part of a simulation pipeline. So as well as my two simple geometric elements, I've got a camera here, which looks directly at my sphere. So if I now press preview, I will see my Radiance. Now this is an R view window. This is a component of Radiance, and it looks a little bit different depending on what platform you're using. I'm on Linux at the moment. So, but I can press, if everything's all white, and this is an exterior scene, I don't have anything I don't have anything covering this, so this is basically outside as far as the simulation is concerned. And if you're doing simulations which are outside, then in the R view window, everything can be completely whited out. So it's a little bit different on Windows for the R view window, but if I press E and enter, then I can pick a point which will normalize the exposure of that image. So if I pick a sort of medium brightness element of the image, then that will become the middle point at which this exposure will be corrected so that we can see geometric detail. Now you'll notice that this sphere in Blender, it's a quad dominant sphere, quad dominant geometry, in that most of the faces are made up of quads. These faces have 4 vertices. We have some tri elements up here, right at the very top, where we only have 3 vertices, but most of these faces are 4. Now that can cause a little bit of a problem when we're previewing how that looks in Radiance. Because if I was to, it's not so bad with this sphere, but if I was to say, if I click on just that top vertex, and I'm just going to turn on proportional editing, and if I now rotate that, and I rotate all my faces. Now these quad faces have become a little bit more complicated. So if I was to look, now that I've edited the geometry, I should re-export my LiVi geometry. And if I now close down this previous R view window and look at it again, you might just see we get these little speckles, we get these little black dots. And this is because this sort of complex, twisted quad geometry is not dealt with very well by Radiance. So the first option that we can select to deal with that is I can select triangulate here. Now what that will do is it will basically, in Blender, I've just now triangulated that mesh. So the mesh isn't made up of any quads anymore, it's all triangulated. Now that's doing it in Blender. This option will do it for the export to Radiance. So the geometry will be triangulated as it gets sent to Radiance. So it makes no difference for the Blender view and the Blender geometry. It just makes a difference for the internal geometry, which is sent to Radiance for simulation. So if I export that geometry again, and I now preview, we should see that those white or those black speckles have gone. And we can see you can sort of see the triangulations in the mesh as well that we've created through that triangulate option. So that's one thing you can do. You can triangulate the geometry in Blender if you want to, but then you've got triangulated geometry in Blender that you then have to subsequently work with. Or you can use this triangulate option to triangulate it before it gets sent to Radiance. The other option is you'll notice that we see the facets of the geometry because the geometry is faceted in Blender, so we see the facets in the Radiance geometry, even when it's triangulated. So another option that I can use is I can turn off this fallback option. Now this fallback option, which is on by default because generally it gives you quicker simulations, but that fallback option sends the geometry to Radiance as individual vertices, faces, and edges. If I turn off that fallback option, then when it's possible, when it's applicable, we now don't send faces, edges, and vertices to Radiance. We now send a mesh to Radiance instead. Now that mesh option has some advantages for us. It's a bit slow to simulate, but it does do some things for us that we can't do before. So if I export that again and I preview, we should now see very much the same thing that we did before. Let me just try and make that a little bit bigger. So we see, yeah, basically the same thing. It's just that instead of sending out faces, edges, and vertices, we've sent out a complete mesh description of this sphere. But the sphere is the same, so it looks the same. But with the fallback option turned off, in Blender, we can select Shade Smooth. And this will, I won't go into the details of it, but this allows us to pseudo smooth shade the object. So the object will look smoother. We might see that a little bit more obvious if I come into rendered rendered mode up here, and I'm in my cycles render engine, we can see we've got smooth shading here. If I turn that smooth shading back to flat, we see we've got flat shading. So we don't change the geometry, we just change how the geometry interacts with lighting. So we can do that within Blender's interface, but if we turn that option on, if I now export and I preview, we should see that in Radiance, we now get a much smoother shading on that sphere. Now we get some artifacts at the boundary where the angle between the surface and the light coming in is more or less perpendicular, but the bulk of the object now looks smooth shaded. So that can be a way of making curved geometry look a little bit more natural in Radiance without making the geometry itself significantly more detailed. So that covers the main options here. Animated, I'll cover that. That's for parametric analysis, and I'll cover that in a separate video. Results points become important if I'm going to now make this sphere into a light sensor. So you'll notice in this LiVi simulation node, I've only got a preview option because none of the materials or none of the objects within my scene have a light sensor attached. So what I might do is I might change the default material to a, actually I'm going to create a new material, delete that one and create a new material. I'm going to call that a sensor. And now in this vSuite material tab down here, which is the same material tab that we set sensor materials up in the previous video, instead of geometry, I'm going to pick a light sensor. So if I now export that, not only do we have a preview button, we also have a calculate button. So I might just go ahead and calculate, and that's pretty quick because it's only simple geometry. And now in my vSuite tab, in my VI display section of this sidebar here, this 3D viewport sidebar that I talked about in the last video, I can now press Radiance Display, and I will now get lighting metrics applied to this material. And by default, I've got lux. So on the bit of my sphere that's facing the sun, I'm getting 57,000 lux. A high figure, which you would imagine is this sphere is out in the sunshine. So now that that sphere is a calculation surface, these other options now become important. So I had faces selected here, which means the center point of each face is the sensor point for the simulation. If I was to make that vertices and export that and calculate that and display that, nothing really different happens. But now the calculation points are the vertices of this surface rather than the center of the faces of the surface. So your results may not look particularly different, but switching between faces and vertices does give slightly different visualization options, which I'll cover. Well, I may as well cover that now. Because I've got vertices selected here, if I turn on VI 3D display and I do and I press Radiance Display, then if I change my 3D level here, I can now kind of make that sphere expand in accordance with how much lighting has hit it. So where most of the light has hit it, that will expand out the most. But if I have faces selected, export, calculate, then with this VI 3D display on again, if I now change my 3D level, you'll see that instead of the vertices moving out, it is now each individual face that moves out from that sort of basic sphere geometry. And this looks a bit weird now, but say you had a flat plane, which was the floor of a room or a desk, and you wanted not only coloration, but you wanted some 3D extrusion of the results, which are in proportion again to the lighting level that hits it, then that's an option that you can use. So that's what faces and vertices does, and I'm going to go back to faces now. Another thing I will show you is if I make this offset value as low as possible, which is 0.001, if I export, calculate, then we might see, let me just turn off VI 3D display. We might see that we've got something weird happen, which is we're getting normal results up here and we're getting normal results down here, but we've got this middle band in this sphere where we're getting no results at all. And that is because these faces, these twisted faces, are now a bit complicated. And it's possible for Radiance to think that the point that we're sensing the lighting is actually behind this surface, behind this face. So what this geometry offset option does is it just allows you to offset the calculation point slightly from the geometric face so that Radiance no longer thinks that the calculation point is behind the face, and it knows that it's in front of the face. So if you get some weird zero result values, then increasing this offset number can help. So that covers sort of the main options within this node. But geometry, the actual geometry, is only one part of the story of the kind of geometric specification for Radiance. The other part of this is the material quality or the material properties. So I'm just going to turn off display. I will just say here while I think about it, you've now got here the original geometry and your results geometry. And this results geometry can be moved and scaled, and you can do whatever you want. It's a separate object within Blender. And that separate object, which will have the original object name with res at the end, will be placed within the LiVi results collection. Now, if you're creating new geometry, so if I wanted a new plane, and this is going to be part of my LiVi simulation, because I had this object selected before, which was in my LiVi results collection, this plane object has gone into LiVi results. So, but you don't want that, because this LiVi results collection is purely for results objects. So I would move that plane by dragging it and putting it into my main collection. But I'm not actually going to use this plane right now, so I'm going to delete it. So just be aware, this is where all your results objects go, and only results objects should be in there. I'm going to get rid of that results objects for the moment. So we have, at the moment, just the default material associated with this sphere and this plane. Now what I'm going to do is I'm going to convert this sphere material from sensor to SUSY. Now, if I look at the plane, which had my default material, then the default Radiance material settings are a plastic material. And in a plastic material, the specular highlights are different from the material color. The specular highlights are the color of the light hitting the object. And that material color is whitish, sort of light gray color with a roughness of 0.1 and a specularity of 0. We can, however, change that plastic material to any kind of material, well, pretty much any kind of radiance material we can think of. And here is a list of radiance materials that are supported. So plastic, glass, dielectric, and there's radiance documentation online that will tell you specifically what all these different materials will do and what they represent. For the moment, I'm going to keep it as plastic, but I'll just change the color to red, export my geometry because I've changed my material specification. Bear in mind, this color doesn't affect the blender geometry. What it does is it affects, oh, I've done it to the wrong object. Let me do it to the right object. So it's not material that I wanted to change. It's the one associated with the sphere, which is Susie, that I wanted to change. And that is now, hopefully, going to show up as a red sphere within our radiance simulation. So we've got you can see the specular highlights are white, which is different from the sphere material itself because this is a plastic material. If I was to change this to metal, export the geometry, preview it again, then now my specular highlight is now colored by the material. It's looking purple because it's probably whiting out a little bit, but you can see if I change the exposure to that point there, you can see the specular highlight is now the same color as the material. That is your basic metal material. Now for those two materials, plastic and metal, this smoothing that I did on my geometry still works. But this smoothing only works in radiance for certain materials. So if I was to convert this to a glass material, export, preview, we should see we've got facets back. And this is because this smoothing method that we can use in Radiance only works for plastic, metal, I think it's only plastic and metal. So translucent, dielectric, glass, light, mirror, that smoothing algorithm won't work. So just bear that in mind. It will then default back to providing, in effect, turning on this fallback option and providing radiance with just the faces, edges, and vertices. This faceted model. So translucent is like frosted glass, translucent materials. A mirror does pretty much what it says on the packet. In that the ball is now a mirror. So reflects the surroundings, reflects the reflects the sky above and reflects the plane below. So in effect, a perfect mirror. But you can see again, it's faceted because the smoothing doesn't work for a mirror material. Light, this will make the sphere emit light. Antimatter will make the sphere disappear. So antimatter can be very useful if you have a sensing surface and you don't want the sensing surface to be part of the geometry of the simulation, you just want the sensing surface to sense the level of lighting, then we can turn on light sensor and we can keep this as antimatter. And then the sensor only calculates the lighting levels, doesn't take part in the, it's not part of the geometric calculation. BSDF I'll cover in a different tutorial. Custom, if we select custom, then we can now select a text file which is registered within Blender's text editor. So if I come into the text editor, we can see here in this text file, which is the text file I've selected here, I have a little material specification written in kind of Blender language. Now the important thing here is that the name of the Radiance description, the name of the material in the Radiance description, should be the same name, and it's case sensitive, as this material in Blender. So Susie is a material in Blender, so I've called this Susie in my Radiance description. So if I was to export that and preview that, I'll now see that Radiance description getting picked up, which was a sort of turquoise glass, turquoise coincidentally being my favorite color, on that sphere. So I think that's most of the things I need to cover in terms of material specification. So, and all these options, again, Radiance documentation will tell you what these different options will do. So those are the options within the geometry node and the sort of material options that go along with it. I'm now going to talk about the LiVi context node. Now the LiVi context node defines the sky, defines the source of lighting or natural lighting for the radiant scene. So by default, when we create a LiVi context node, we will have a basic context, which is the only one I'm going to talk about here. We also have a climate-based daylight modeling context, which I'll talk about in another video. But we have a basic context, and for that basic context, there are different methods I can use to generate a sky. So the default one, the first one, is GenSky, which is a Radiance program to generate simple black and white skies. So these are good for just doing numerical values, so fine for that. And within that GenSky program, we can create a sunny sky, partly cloudy, cloudy, or a daylight factor sky. I'll come to daylight factor sky in a little bit more detail in a moment. So while I've got a sunny sky selected, then, or indeed partly cloudy, then I can now change some options for that sunny sky. So I could, for example, change the ground reflectivity. So if I now export that context and I now preview that, we should now see that I now have this green background because I'm looking down slightly with my camera and I'm seeing the ground behind the sphere. And because I've set now a little bit of reflectivity on that ground, I can now see that I get a green ground in the background. And that can be changed to whatever color you want. I can also, because I've got a sunny sky and the position of the sun in the sky is now important, I can now change the time and the day for that particular sky position or sun position. So if I zoom out, we'll see I've got a blender sun here, and that has been positioned automatically according to my time and my date. But if I change my time, or if I change my date, I will automatically get an update on the sun position within Blender. Now this can be quite useful because if I'm in this solid shading mode and I've got shadow turned on, then I'll see that difference in shadow sort of in real time in Blender's viewport. If I come into rendered mode, I can do the same. So that's kind of an easy and quick way to get sort of instant feedback on what this sun position means, or what this time and what this day means, in terms of where the light and shadow is going to land within your scene, within your geometric scene. Animation, again, cover that. It's about parametric analysis. I'll cover that in a separate video. Turbidity is a value which pertains to Gen Sky. So if you look up Radiance documentation for Gen Sky, you'll find out what this turbidity value does, and it's basically about levels of light pollution. If you're in a sort of context which is incredibly clear skies, you're out up in the Alps or something, then this turbidity value is a certain value. If you're in a very smoggy city, this recommended turbidity value will be different. I can't remember, I must admit, off the top of my head, whether a clear sky is a low value or a smoggy sky is a low value. But there's plenty of documentation online for that. This final option, which will exist for kind of irrespective of some of the options you've got set up here, this final option, HDR, will create a high dynamic range image of the sky. So if I now click export, this will take a little bit longer because I've now generated an HDR image of that sky. So if I go into the project directory, so I'm in my Blender 28 bunny shadow is where my blend file is saved. If I just come into that folder, if I come into that folder, bunny shadow, then within that folder, I'll see now two high dynamic range images. I'll see one which is kind of a spherical picture of that sky, just the sky on its own. So you've got the sun and the sky and the ground. And I'll also have a latitude or longitude or sometimes called polar mapped. So you could use this in Blender if you wanted to visualize in Blender with this sky, then you could use this as an environment texture within Blender to visualize in cycles how this radiant sky will look. This HDR option becomes a lot more useful when we do a CBDM analysis, which I'll do in a separate video. I'm going to turn it off because it takes a bit longer to do an export with that turned on. So those are the basics of Gen Sky. Partly cloudy, we get the same options. If we go to cloudy, we get the same options. If we go to DF Sky, then a daylight factor sky is a sort of homogeneous cloudy sky, so sun position doesn't matter. So all those options disappear. And I'll just, if I do a sunny sky again, and I make my sphere into a sensor again, then if I now calculate that, and I press Radiance Display, we'll see that we've got some metrics up here. So I've got lux. I also have watts per meter squared. Watts per meter squared in the visible spectrum, which is an important distinction. So this is, the visible part of the spectrum that we can see. This is the wattage per meter squared landing on the sphere. And we also have watts, which is the wattage landing on each of these individual faces. So because each face is less than 1 square meter, I get lower values. That's just the wattage landing on that one and the wattage landing on that one. So if I was to change this to a daylight factor sky, export, calculate, and Radiance Display again, I now have daylight factor as the metric that I'm projecting onto that sphere. But daylight factor, you could convert this into lux by, for example, changing my legend title and then modifying it by 100. This will give me the lux value because daylight factor is derived from lux. But I can also plot out the watts, and I can plot out the watts per meter squared again as a result of that daylight factor sky. If I come to Gen Daylit, most of the options here are the same. We have now, instead of turbidity, we have epsilon and delta. These are two radiance parameters specifically for the Gen Daylit program, which is also built into Radiance. So again, refer to the online documentation because they will define whether it's a sunny sky or a cloudy sky, etc. We also have a new option here, color sky. So with Gen Daylit, we can now produce a colored sky. Now, because my camera angle isn't looking at the sky, but hopefully you can see it, it's a little bit bluish now. In fact, I could change my camera viewpoint, so I'll just look at the sky for a moment. So I've only changed the camera viewpoint, so I don't need to re-export my context or my geometry. I could just have a look at the sky. And again, I'll need to change the exposure because I'm looking directly at the sky now, and we can see we've got a blue sky. So yeah, Gen Daylit does allow you to do colored skies. HDR option does the same thing, and the time and the days, they all do the same thing as well. I can use an HDR sky. Now, the HDR sky I produced earlier, I could use. Now, there wouldn't be a lot of point in doing that because it's an HDR sky that's generated from Radiance, which would be used in the simulation anyway as a Radiance sky. But we can take HDR skies off different websites. So, for example, let me just see if I can remember where I put some skies. Wasn't there. wasn't there, although that will do. So I've now picked an HDR sky. Now if I come to Blender's image editor, and what did I pick? Untitled HDR, which I've loaded up a number of times into this, and I've got to find the right one. I guess it's the last one. So that's the HDR sky. So somebody's generated this HDR sky from a real scene, and I believe I got this one from HDRI Haven, which is a great website which has free HDR skies that we can use. They need to be in Radiance HDR format, and once I've loaded that HDR sky, now this is in what's called polar or latitude longitude format, which I select here. Angular map is a slightly old school HDR mapping, which isn't used so much anymore. Polar is the one which is by far more common, and that is what this one is in. Angular ones tend to look like fisheye images, and this is a rectangular image. And when they're rectangular, that generally means they're in polar format. So I can export that, and I'm now looking at the sky within Radiance, so we can see that I'm now seeing that little part of the sky. If I come back and look at my sphere and preview that, we can see now that that HDR image has been wrapped around that Radiance scene. Now you'll notice we get real speckles here. Now that's one disadvantage with certain kinds of HDR image that we might wrap around our Radiance geometry, and that is because Radiance finds it hard to find the light source, the strong light source, which is the sun in this image. So if this was a cloudy sky, this preview would work really well, but because I've got a really strong directional light source in this image, Radiance can find that a little bit difficult to find, and we get this speckled visualization. Now you can improve on that by increasing the accuracy within this simulation node. But you have to turn it up insanely high to get that sunshine to appear sort of properly within that Radiance scene. And I'm not going to do that here because it would take a very long time to make that to do that calculation. So, but that's the basics of HDR sky. I can do Radiance sky, which, like a Radiance material, allows me to pick a text file. This time I pick a text file from my hard drive. I'm not picking a text file from Blender's text editor. But that text file can then contain a custom description of the Radiance sky. And I'll refer you to online documentation about Radiance as to how you might, in text file format, describe a Radiance sky. And the last option is none. So there'll be no sky. So this would be useful for when we're doing an artificial lighting calculation, for example, and we only want to know what the artificial lighting within the scene is. And I'll cover artificial lighting in another tutorial as well. So this is, effectively at night. There's no brightness in the sky at all. So that covers most of the LiVi context options, I think. In terms of LiVi simulation options, we have this frames 1:1 text here, and this just tells us, because I'm in frame 1 at the moment in Blender. Blender's an animation suite, so you can, if you use your left and right arrows, you can see this number changes. So I'm skipping between frames. I have no animation set up in Blender, so it doesn't matter. but I did all my exporting on frame 1. So this geometry pertains to frame 1. This context pertains to frame 1. So in my LiVi simulation, it says, right, we're simulating frame 1 to frame 1. If I had an animation set up here or an animation set up here over a certain frame range, then that frame range would be represented here. Photon mapping is a sort of advanced technique, and I will cover that in a different video. Accuracy, I've had it on low to keep things nice and quick for this video tutorial. But we've got medium, high, and we've got custom. And if I select custom, then I can put in custom radiance parameters in here. So minus AB would be ambient bounces, so I could have 3 ambient bounces. Minus AD would be ambient divisions, so I can have 5, 1, 2 in there. And I can then calculate that, or I can preview that with these new custom parameters. So you have to be a bit careful with custom parameters, or you can get slightly weird looking results as I've got here. If there's something wrong here, so I've got a gap between my A and my D, then the option to preview and to calculate will disappear. So as you can imagine, as these go up, we get better results, more refined results, but the simulations will take longer. Camera, this allows me to select the camera. So I've only got one camera in my scene at the moment, which is called camera. But if I had multiple cameras from different perspectives, I could select that camera here. And yeah, the preview and calculate buttons, which I've covered. So yeah, I hope that I haven't done any sort of real world architectural examples here because I just want to focus on the options within these nodes. But I hope that kind of given you the sort of basics of how to construct a LiVi simulation. In subsequent LiVi videos, I'll probably talk a little bit more, in terms of a genuine or slightly more architecturally relevant kind of example. But here, yeah, I just want you to know the basics of the options within the nodes. And yes, hopefully I've done that. So let me just check that I think all the options in here are the same as the previous video where I did sky view factor and shadow mapping. We got some slightly odd results because of this AB custom parameters that I've used, but the options here are all the same as in the previous video tutorial. So if you want to know what all these options do, then I'll refer you back to the previous video because it discusses them all there. Yeah, I think that's everything for now. Okay, thanks for watching.